Hello everyone, welcome to the MIF++ seminar. We are back to Zoom, and today it's a great pleasure to introduce Professor Keith Butler from University College London, who will talk about learning and steering the language of crystal chemistry. So Keith, over to you, please.
Well, thank you very much for the introduction, Vitaly, and thank you also for the invitation to come and speak at this very interesting series of webinars that you run. And of course, I've been a keen follower and a fan of the work that's been done at the MIF for many years now. So it's a real pleasure to come and speak to people here. And I think you'll see probably from the stuff that I talk about that a lot of the work that we've been doing in our group over the years is very closely aligned to a lot of the work that's been done at the MIF. And I know we certainly take inspiration from the work that you guys do. So it's really nice for me to be able to present some of the stuff that we've been working on. So I'll talk a little bit about some kind of, well, mostly it's about representations for materials and how we're using them for discovery generally. And there's a little bit of learning representations. There's some stuff on autoregressive generation. There's a little bit of stuff on optimal transport towards the end. And hopefully there'll be something in there that's interesting to everybody tuned in for this talk today. So before I jump into the talk, I just want to quickly acknowledge the people who've done most of the work that I present here. So Cyprian, Lewis, Quang Dai, and Ricardo did a lot of the work on the autoregressive generation, which I'll talk about later. Matthew has been doing the work on optimal transport and materials discovery, and Hyunsu, Aaron, and Anthony we worked together on some of the work that comes towards the end of the learning representation stuff that I'll talk about at the start, and of course the various people who've kindly funded the research and made it all possible. So yeah, let's start with motivating ourselves with trying to build representations for materials. So what we're interested in is essentially trying to learn some kind of function to predict properties. So in our group, we're interested in discovering new materials, and it's new materials with some desired property. And we would like to be able to take any material and quickly work out whether it has the desired property or not. So we want to learn some functional mapping, f of x to y. And the question that I guess most of this talk will be concerned with is, what exactly is that x? And as we know, I mean, in chemistry, if we go back throughout the history of chemistry, there's a rich history of building different types of representations for chemicals and materials. There's symmetry, there's the Mendeleev table, there's these kind of stick diagrams from organic chemistry, and these are all extremely useful and extremely rich representations which allow people to work with these systems and to understand them. They're not necessarily extremely well suited to using computers, because that's the other thing that I personally and my group are interested in. We want to do chemistry on computers, and we want to use computers to do numerical experiments to help us to discover new materials, because we hope that will allow us to explore more options than you can ever do experimentally, and it will allow you to do that at a lower cost than it would be to do it experimentally. So what we really want is some way to try and build representations that are useful for computers. And of course, as most of us will know, the better you build your representation, the more kind of relevant information that you have contained within this f or within this x, then the less work you have to do with f to make a prediction of y. So your training your models becomes a lot easier if you have a good representation. So the first thing I'm going to talk about is some work we did a couple of years ago, and this was led by Lewis during his PhD, and this was on building something called distributed representations for chemical elements. And so just in case anybody's not fully au fait with the language of different types of representations, I'll just quickly introduce and motivate distributed representation. So kind of the easiest way to explain what a distributed representation is to explain its opposite, which is a localist representation. So let's imagine we had some data set here and it had these 6 different animals in it. And I want to generate a localist representation that allows me to have a label or a label for or a representation for any animal that occurs within my data set. So the easiest way to do that with a localist representation is say, well, I have 6 animals. I'll have 6 entries within my vector. And if the animal corresponds to that animal, then that entry will be 1 and everything else will be 0. So it's what's known as one-hot representations. So we have here a bear, and of course, bear is turned on and everything else switched off. So that's quite intuitive, quite an easy way to build a representation for my data. Another way to think about it, so a distributed representation, we might think that rather than just having an element of the vector for each creature within our data set, maybe each element within our vector is some attribute of the different creatures. So in this case, we have things like walk, swim, fly, egg, claw, wild. And then you essentially distribute the values across that vector. And if you read off the different, so we see here, the bear definitely walks, it does swim sometimes, it's pretty wild, and it definitely has claws. And so we're able to read off that representation. We go, oh, that corresponds to bear. And then tiger has a different representation and so on. And the point here being that the information is distributed across the vector. And so why would we want to do this? So kind of somewhat intuitively, the localist representation makes more sense. It's easier to get your head around. But the distributed representation turns out to have many advantages compared to a localist representation. So the first advantage that I can offer to you is, let's say we had a new animal. Let's say we had a dog, and we want to include it into our data set. So we include a dog. Now, if we're working with a localist representation, we suddenly need to add a new element to all of our vectors, and we need to refeaturize our entire data set and change the way that our data is represented just to accommodate the fact that there's this new creature. And it means that we couldn't represent that creature without changing our representation. Whereas within our distributed representation, it quite naturally fits. So distributed representations are much more extensible. So they're very nice in that way. They can handle unseen classes. Another advantage, and this is maybe the more important one from our point of view, because let's say we're working with chemical elements and we don't expect new elements to turn up. The really important and useful advantage is that the notion of distance in the distributed representations is meaningful. So you could say, for example, the frog is more similar to the fish than it is to the bear. Because the attributes, you can calculate some metric and the attributes tell you how far they are apart. In the localist representation, everything's equally spaced. So you have no idea of what's similar to what. And that's super useful for when we want to build a model. So having some idea of, hydrogen is similar to lithium. It's more similar to lithium than it is to silicon. That's a useful thing to know. We'd like to capture that in a representation of chemicals. So how are we going to do that? So a way that people have done it kind of previously to the work we were doing, a lot of the work that people did was you construct vectors based on the elemental properties. And then you just simply, if you've got a material, then you just add them together in the stoichiometric ratio and you get your representation for the material. And that is quite useful. That is a useful way of building a distributed representation. But actually, we were interested in taking these ideas from natural language processing that say that you don't even need to put those kind of inductive biases in. You can actually learn a representation by looking at the data you're interested in representing and looking how it occurs. And to kind of exemplify this, is a famous example about from natural language, based on this distributional hypothesis, which says you know a word by the company it keeps. So the example here is we have this sentence saying Marianne saw a furry little whoppamink hiding in the tree. And the point here is the word whoppamink. That's a made up word. So hopefully nobody knows exactly what a whoppamink is. However, if I asked everybody in this meeting to draw a picture of what they think a whoppamink looks like, they're probably going to draw something relatively similar. And the reason for that is that you've looked at the context words, and that tells you, oh, this is what a whoppamink probably is. So the context basically defines the words. And this is the work that Lewis did, was taking this forward to atoms. But first of all, let's look at how you actually extract that representation for words. So one of the methods that's used anyway in natural language processing, and the one that we adapted, is something called skipgrams. So you take your corpus and you basically build localized representations. So let's say we want to learn a representation for this central word, which is this. And we have some localist representations of our entire corpus of words, which are relatively small here. We see these one-hot vectors. But we feed in the the localist representation of our word this, and then it passes through a neural network, and there's some representation in the middle. And that representation then passes through another neural network, which attempts to predict the localist representations of the two context words. And you can make it more context words. You can go out to any distance you like. But essentially then you train this network over a large corpus of text. And at the end of it, you've developed some compressed vector here in the middle, which has a distribution of values across it, which is a distributed representation of the word, of the various words in your corpus. And so this is what Lewis did, was to adapt that idea and take it forward for learning representations for elements. And so how do you do elements like sentences? Well, essentially we build graphs of the materials, and if we're doing nearest neighbors, first nearest neighbors, then you just look at the nearest neighbors of them, and from the localist representation of, in this case, barium, you try to predict these nitrogens that are bonded to it, and you kind of loop through the whole data set, and you compare your outputs to the actual output, and you calculate some cross entropy loss, and you just minimize that across your full data set, and you end up with your distributed representations for all the materials, which we can then take a look at here. So what we've done here is then we've taken those learned representations and projected them down into 2 dimensions, just to see if there's some kind of, if there's structure within what we've learned. And it does look like, from our chemical knowledge, it's learning a lot of the trends you'd expect. So sulfur and selenium are close together, oxygen and fluorine are close together, nitrogen's fairly close to there. I mean, this is exactly what you'd want from chemistry, but it's also kind of what you'd expect from the way this is trained. I mean, all this tells you is that sulfur and selenium tend to co-occur with the same atoms in the same kind of environments, and that's exactly what we'd expect. Again, you have your ions down here and stuff like that. So that's quite nice. These T-SNE maps, or these reduced dimensionality maps, can be quite nice for getting out these trends. Of course, I think you can sometimes read too much into them, and sometimes I say it's a bit like, reading tea leaves or something when you read these T-SNE maps, because you can see what you want. But I would argue there are some reasonable qualitative trends there anyway. But the real proof of, we wanted to develop these representations to make the models work better. So we basically went and we've done some benchmarking of training models with these representations and compared them to other atomic representations. And so on this table here, everything on these three representations at the bottom are all basically composition only. So R1 skip atom is also composition only, and it essentially across pretty much all of the tasks, it's the best of the composition only representations. Now, when you have access to the structure, you start doing better, but that's something I'm going to come on to later in the talk. But essentially, I think what this shows is we built a pretty good representation for the composition of materials, or a pretty useful one. not the final word by any means, and I certainly know there's been nice work done at MIF to come up with other representations. But this is one way of doing it, and I think it's quite useful, quite a nice way of learning representations. So some work then that we did with Anthony, who was a PhD student with Aaron, who I was helping to supervise, was to kind of extend this idea. So we had skip atom, and essentially what Anthony did, one of the things during his PhD was to extend that to skip species. And so that's, instead of having it just granularity of atoms, it's an atom plus an oxidation state. Because of course we know that often in materials problems, the oxidation state of the atom will change a lot. So like tin in a 2+ oxidation state is actually a very different beast to tin in a 4+ oxidation state. And so maybe that information is useful. And Anthony developed this skip species and essentially tried it on a number of different tasks. And so something interesting we found here is that so if you're trying to predict formation energy, it actually turns out that species information didn't make the model an awful lot better. So in green you have the skip atom, whereas in blue you have the skip species. But if you're looking at something like band gap, then you see you get a very noticeable improvement by including the oxidation state. For classifying whether something's a metal or not, so here higher is better. And in those cases, again, having the species is useful. And for magnetic classification, magnetic certainly makes sense. I mean, the spin on the atoms will completely depend on the oxidation state. So you do a lot better with having some information about the oxidation state. And then with Hyunsu and also with Anthony, something we did was to kind of use these representations and the kind of fact that you can map out the space to do some a little bit of a taxonomy of material space. And I don't know, people are famous with the famous Donald Rumsfeld taxonomy of unknown unknowns and known knowns, and it's something a little bit like that. So we kind of looked at the materials project space and we came up with these 4 classes. So there's standard classes, and this is any material which is, I should say, I need to explain here what allowed means. So we have a chemical filter. So this is based on another code that we have called SMACT, which basically looks at materials and checks if their kind of oxidation states and stoichiometries make sense and whether they're chemically sensible composition. So we looked at standard materials. So these are things that are allowed according to our SMACT criteria and are known. We've then got missing materials, which are things that the chemical filter allows but aren't reported. Then we've got interesting, which is things that the chemical filter says are forbidden but are actually known. And then there's unlikely things which are forbidden and are unknown. And using that, we can kind of build up these maps using that in combination with representation. So we've got skip atom here, but we've also got some other representations. We've got the magnet representation as well, and different ways of doing the dimensionality reduction. And it's nice because you can build up these maps and kind of look for trends within your chemical space. And actually, the main thing that we got from this was we were kind of able to get some idea of what these so-called interesting materials. So these are the ones that our SMACT filters were saying they shouldn't be allowed to exist, but they do exist. That's the ones in green here. And if you try and compare it to the, so this is the chemistries are plotted here. So somewhat unhelpfully, they're all called gray. They're gray, which is called others. But actually, if you look at it, most of those materials actually turn out to be they turn out to be intermetallic materials. And it led us to realize that actually these SMACT chemical filters that we've developed for trying to search through material space, we developed them really from a very polar ionic material point of view. And so we realized that actually a lot of the kind of the heuristics that we use for searching through that space are not really applicable in intermetallics, where you don't get the kind of nice discrete concepts of charge state. And that's led to new work that people have been doing to try and build rules for intermetallics into SMACT for screening. Okay, so far I've talked about looking at compositions, but I kind of alluded to the fact that, of course, if we know more about structure, that's even better, because it allows us to get better fidelity in our predictions. And so this will lead me on to talking about some other work that Lewis led during his PhD, which was to develop this autoregressive model for generating crystal structures. And so just a quick overview of what we mean by autoregressive. People may well be aware, but autoregressive basically means that we feed in some kind of string, whatever it is. Let's say if it's text, then that string is the beginning of a sentence. It passes through your model. Your model predicts what the next word in that sentence is going to be. And then you take that full string and pass it back into the start and predict the next word. Hence the term autoregressive. So you're just going around and around and in this loop. And this is what's behind GPT and pretty much all of the modern large language models. And it's kind of impressive that such a in some ways I find it an extremely naive mechanism, but if you just train it on enough data, it turns out that it does do some very interesting things. And Lewis's idea was to try and adapt this for predicting crystal structures, and it's I mean, it's a really clever idea, I think, but it's nothing like, it's not a huge conceptual leap. He just said, well, let's take an autoregressive model and train it on CIF files rather than on text, and see if it can work for crystal structure generation. And the nice thing is that you can build a CIF file such that the first line is the composition. So you can imagine then you can just start off with this composition and try and learn the structure autoregressively. So basically you train the model by, say, putting in this composition, getting it to predict what the space group and so on should be, comparing your predictions to the true CIF, and getting a cross-entropy loss that you minimize across some data set. So Lewis built about 2.5 million CIFs to train this model on. And initially, I thought this is not going to work, because I thought the mechanism is too simplistic, and you couldn't possibly learn the vagaries of crystal structure generation by doing this. But I have to say, Lewis really proved me wrong on this, and it works surprisingly well. And so when you come to actually using the model, as I said, you basically you prompt it with that first line. The LLM goes off and keeps generating new tokens, and it keeps doing that until it generates these 2 end-of-line tokens. Once it's generated the 2 of those, it says, right, I'm done. I've generated you a full CIF. Here you go. You can take a look at that CIF in your favorite visualization software. And he's also written very nice, just a very nice package around it. So he's made it very easy to use. So you can get the package here from his GitHub. You can he's got commands to like build the prompts that you want. So you can even build like strings and strings of prompts. So you could have millions of formulae that you wanted to generate, and then you just feed them into the model, and it will generate them and give you some crystal structures. And so you can actually, even if you like, you can go and there's a web app. And actually, recently we've been updating the web app, so there's a new version, Crystal LLM Pi. I'll talk about Pi in a couple of minutes. But if you like to go and try out the web app yourself, you're welcome to go to this URL, and you can spin it up, and you can type in a formula, and it will generate you a CIF file that you can download if you want. Of course, this is mostly for playing with. If you really want to use it in research, you probably want to download the code yourself. And actually, I should say, we're also working on, we've got some containers as well. So if you want to just get the code and not have to worry about dependencies and building it yourself, we're soon going to have some containers up on the PSDI website. And if anybody's interested in that, feel free to email me afterwards. But yeah, Crystal LLM Pi. So Pi, what does that mean? So Pi here stands for property injection. So at the moment, we've got a Crystal LLM which can generate new structures from a composition. That's nice, but we're now interested in, can you kind of try and direct that? So can you say, I'm going to give you a composition, but I want you to generate me something that has good thermal conductivity, like a certain value of thermal conductivity or something like that. So that's what property injection is about. And the way we do that is, this is work that's been done by Cyprian, and he's been introducing what's called conditioning into the generative process. And so what do we mean by conditioning? So to introduce conditioning, I went to my, well, maybe not my favorite, but the large language model, which I have a subscription to, and I asked it to generate me a description of the MIF++ webinars, and it's clearly gone and found your website and scraped some information off it and generated me a nice slide ready description. Such GPT language, right? Slide ready. It always says things like that. It loves a hyphen. But yeah, so it's generated me that description, which is great. Then I said, okay, well, let's condition that generation. So can you generate me a description of the MIF++ webinars conditioned on working in the style of metaphysical poet John Donne? So it's gone off and done that. So it's tried to use that same information, but now with an extra condition of I'm trying to sound like John Donne. And it starts off with this nice line about no discipline is an island entire of itself. I would say that any time you ask GPT to condition on John Donne, it always starts off by saying no, X such and such is not an island. It seems to that is what John Donne does according to GPT. But anyway, it's quite a nice kind of representation of John Donne's style being applied to some new text. So, and that's kind of done by introducing some kind of conditioning. And so what Cyprian's done is to work on a way of introducing conditioning into the Crystal LLM generative process. And I won't go too much into this, but he's looked at some different mechanisms, and where the kind of technical difficulty lay here is that when you're doing autoregressive prediction, you're basically working on discrete tokens. So it's kind of a classification problem, if you like. But often when you want to condition on some property, that's usually a regression problem. You've usually got a continuous value. So he's looked at different ways of introducing continuous values, and also looked at ways that you can introduce this conditioning in such a way that you kind of preserve the information that you've learned in pre-training. So you pre-train Crystal LLM on these 2.5 million CIFs. And you don't want to learn all of the nice, you don't want to lose all of the nice stuff it's learned there when you're trying to fine tune it on some small set of conditions. And so that's another thing that these mechanisms that Cyprian's been developing try to handle. So they try to encode continuous values, and they try to do it in such a way that you preserve as much information from the pre-trained model as possible, so that you can then actually do this conditioning with a relatively small data set. So with 1,000 or a few thousand labels, you can do fine tuning to do conditioned generation. And just to give you some examples of the conditioning in action. So the example here is that we condition on target densities. And so in gray in the background is kind of distribution of the densities of the training data set. And then you prompt the model Crystal LLM and you say, generate me new materials. So we don't even give it a composition. We just say any new material, but on condition of a density of 1.27 grams per centimeter cubed. And you can see the mode of the generated material shifts nicely to our target. And likewise, when we go to higher densities, you see the mode of the generated distributions moving. There's lots of other information there. So you see when you fine tune it on less data, you get less of the desired behavior with moving to the places that you want. And that depends also on how far outside the distribution you're going. So when you go really far into the tails of the original distribution, you really need to have quite a lot of fine-tuning data. And I think that's just because it needs to see some examples. Like I'm not sure these models actually generalize far beyond the trained distribution, but that's something we'll talk about a little bit more in a couple of minutes. So something else we've done is to try and condition it not just on properties that you might like, but something we're particularly interested in is can you condition it on experimental data? So often you'll do something like you'll know what the composition of a material is. You'll go and make an X-ray diffraction measurement, and the X-ray diffraction you'll be using to try and solve the structure of your material. And so we've done some work to try and condition the model on experimental X-ray diffraction data, and this is just kind of zooming in to show that using the XRD data actually does improve the predictions that you get. You get better R squareds on the lattice constants, particularly the Z constant and the volumes and things like that. So it has a good effect on making the model predict the structure better. And you can imagine building this then into experimental pipelines where you have this in some kind of autonomous laboratory that's doing XRD measurements and then trying to generate candidate model structures using a generative model data. And this is an example of doing it for a property, so trying to discover a new photovoltaic. So here we're conditioning on having a high SLME. So SLME is a kind of a metric that, or a measure that you can calculate from the electronic structure of a material that will tell you what the maximum efficiency it can have is. It's related to the detail balance or Shockley-Queisser limit that people may be aware of, but it takes into account a bit more nuance of the electronic structure of the material. But anyway, so what we've done is we tried to condition Crystal LLM to find some high SLME materials, and you can see that when you prompt it with the looking for the high SLME, so the training distribution is in red here, and in blue is our generated distribution. So we're getting these higher SLME materials, and we've actually taken some of these forward and done DFT on them, and by doing DFT then have confirmed, I should say hybrid DFT, so relatively accurate electronic structures, confirmed that these are indeed high SLME materials. And there's a number of new materials that previously haven't been looked at as photovoltaics, which we think could be kind of interesting coming from that kind of study. But so a couple of questions then about these autoregressive models. So one of the things that we talk about quite a lot, and I know within the group we have different opinions about this, but about whether these autoregressive models are really, I mean, are they just learning underlying correlations, or are they really developing some kind of world model of your systems? And to kind of illustrate these 2 points of view, I've got this example here. So we've got a sentence: the glass fell off the table, and we're trying to predict the next word. So if you're kind of on the stochastic parrot side of the argument, you say, well, it's just learned the distribution of all the tokens, and smashed is the most likely one, and maybe spilled is also relatively likely, but filled is very unlikely. It just draws from this distribution. These are just correlations, and it'll predict a word based on that. If you're more from the kind of world model, AGI, galaxy brain kind of side of the argument, you think that you would say that these models, by learning on so much data, have started to build some kind of internal representation of the world, and so they might have some idea of the laws of gravity, which tell you that falling off the table means you're going to go down. They'll have some idea of what the chemistry of glass is and how this relates to the mechanical properties of the glass, and then use all of that to come up with the next word. So we're kind of interested in, are the models actually learning world models, or are they just doing kind of correlations in high dimensions? And so one of the things we've done is to try and find data that's kind of outside the training distribution. And I should say that this was relatively hard because Lewis trained it on a lot of CIF files, but we scraped around and found some kind of things like clays, which are not very well represented in the training data, and brand new ones that weren't in the training data. And I think the important line here is the matched unseen compared to the valid structure. So valid structure is the kind of the normal test set that we would have used, which was just a split of the training set. And you see that getting the structures matched is much lower on these unseen data. So I think there's not a huge amount of generalization way beyond your training set. And another thing we did was like, well, we could try and rediscover zeolites. So there weren't many, if any, zeolites in the data set. So zeolites, if people aren't aware, are kind of microporous aluminosilicate materials. So they form these three-dimensional porous structures from SiO2 or silicon and aluminium oxide. So we basically prompted crystal Pi with SiO2 formula and a very low density. And it comes up with things like these layered materials, which is fine. I mean, that is what we asked for, but it's definitely not rediscovering zeolites. These don't have the three-dimensional porous structure. So, I mean, I'm somewhat skeptical about this world model hypothesis, and I'd say I'd need quite a bit to be convinced. But that's not to say these models aren't super useful. I mean, you've learned the distribution of condensed inorganic materials, which is already an extremely useful space to know about. And you can condition it on experimental data and try and predict structures and things. So you can do tons of useful things with these. I just think we need to temper our ideas about just how much new science these things actually learn. So that's one limitation of these. And another I think elephant in the room, and this goes right back to the what I said at the start. I said we like to use computers to look at new materials, and we like to do that because we think this is a lower cost way of discovering new materials. And also, I should say, in our group, we're generally interested in green and clean energy materials. And one thing we all know about compute and machine learning and big AI models is that they use up a lot of energy, right? That tends to be one of the big bottlenecks on any of these models is there's an energy bottleneck on just how much energy you can have to run it. So, can machine learning really is it justified to use machine learning if we're trying to discover new clean energy materials? And this is something we looked at a bit with we've been looking at with discovering new photovoltaic materials. So we kind of looked at replacing standard density functional theory with machine learning at different levels within a discovery workflow. And then we've used this Code Carbon package, which allows you to track the carbon emissions of your calculations. And essentially, we've tried to correlate the carbon emissions of a discovery process versus the accuracy of that discovery process. And here on the left, we essentially have a bunch of different discovery processes. So the highest carbon emission one here is all high quality DFT, so all hybrid DFT calculations. And then there's other things like you can do all GGA DFT. You can do machine learning with some DFT. That is all high quality DFT as well. You could do it all machine learning. And you can see you get different footprints, and then we compare the kind of accuracy. So in these Pareto fronts on the right hand side, it's basically plotting the mean absolute error versus the gold standard data set versus the relative carbon costs, and you see some definite trade-offs, and it also gives you an idea. There are some kind of approaches that we have in here, which are things like using machine learning to learn the spectra and calculating the SLME from that. That turns out to be way off the Pareto front. I really wouldn't recommend doing that, certainly not with current models. But you can kind of choose your accuracy versus your carbon cost, and I think these are useful things to know when we're really trying to critically think about whether what we're doing is worthwhile for the task that we're trying to do. It's really important to be able to take these kind of things into account. And so, yeah, and another point from that is that I found really interesting is that the machine learning isn't perfect, but we compared the rank correlation to a kind of low quality DFT with a different functional, and actually the rank correlation from the machine learned models is significantly better than using bad DFT. So machine learning not perfect, but it's better than bad DFT. So the final few minutes of this talk, I'm going to talk about some work that Matthew's been doing, and this is to try and use some methods that kind of almost sidestep doing really heavy machine learning at all. And the idea here is to try and look at pre-existing databases, and taking inspiration from high quality materials that we already know, and see if we can use them to like search in these databases to find new materials that are similar to our materials. And no, this is very similar to some of the work that you guys have been doing as well. So hopefully it's of some interest to you. And we use this optimal transport method or theory to to map the distances between any two materials. And so essentially optimal transport is solving the problem of converting one distribution into another one, and what's the smallest amount of work you have to do in order to do that. So what Matthew's been working on is a method that he's borrowed from the literature. So it's a method that was developed just kind of abstractly for graphs, I would say. And it's about doing optimal transport, but for comparing things with graph structure. And so the main concept here is that you calculate this, what's called a fused Gromov-Wasserstein distance. So you've got a normal Wasserstein distance, which is this m here, which tells you about the distance, or the optimal transport between the nodes or the elements within your material. And then you've also got a distance, so this is the Gromov distance, which characterizes the distance between the graph structures. And then you just got some balance between them. This alpha factor gives you some balance between the two distances. So you can say, oh, I want to look more at graphs, or I want to look more at compositions. And this is just Matthew's development of this FGW method for crystals. And this is an example. So taking a simple example from chemistry, you can look at zinc oxide. And so if you look at the composition only, so if we go back, this is essentially saying we set alpha equals to 0 here. So we do all composition in our distance. Then you find that this differentiates between zinc sulfide and zinc oxide, but not between the two polymorphs of zinc oxide, which is kind of what you'd expect, I guess. Then if you set alpha to 1, so you do pure Gromov distance, then the Wurtzite structures of zinc sulfide and zinc oxide are identical, but the zinc blend is identified as different. And then if you do something in the middle, you can resolve all of the compositions and the polymorphs. And so Matthew's then taken this and done some clustering. So he's taken a data set of materials with calculated SLMEs, and he's kind of essentially used some k-medioid clustering to cluster that data set and pick out the highest representations, efficient structures from the different clusters within the data set. And you see, it gives you a nice spread of very different types of materials. So you've got some layered materials here. You've got this two-dimensional materials here. There's a bunch of different kind of systems so it gives you this nice diversity in kind of in chemical space. And interestingly, there's one of the clusters that picks out this zinc sulfide cluster, which actually everything in it has really low, really low efficiency, which is quite an interesting cluster. But then he's also used that to go and explore a larger data set. So first of all, we looked at, so if you take these seed structures, so these 12 seed structures, and if you then try and look at the materials close to them using the FGW distance, then do you shift to higher efficiencies? So if you choose a starting material which is an efficiency, very high efficiency up here around 28%, and then we use this FGW to explore the space around it, you can see the distributions do get shifted away from, so the base distribution is in black, and depending on the different representations we use, so we tried a few different representations for the composition, but all of them do kind of shift the distribution towards finding more high SLME materials. It's not perfect, but it definitely does shift it there. And then Matthew used that to kind of calculate it across the entire materials project data set. And then we're able to propose a bunch of new high SLME materials, which again, we've taken forward and done hybrid DFT. And we found some interesting new candidate materials that, so for example, this cesium antimony material, which haven't been explored before for photovoltaic, but actually look really promising from the calculations that we've done so far. Okay, so I think it's about time for me to summarize. So I would say that learning representations is a powerful way to leverage chemical databases to help with discovery. I think that I'm still amazed that next token generation is able to do structure generation at all, like effective structure generation. It's pretty impressive, but we're always data bound, and getting data is expensive, and computational methods for discovery are more expensive than we'd like to admit often. So I think there's a lot of space for this looking at smart searching methods so that we can get the most value from the data that we do generate. And with that, I'd just like to thank you all for your kind attention.
Eve, thank you. Sorry, my internet was slow at that moment. Let us thank Keith for the nice presentation, please. Physically or virtually.
Thank you.
Yes. Yes, I'll stop the recording.